Welcome to the AI Research Roundup. I am Alex, and today we're looking at a paper from the Papers with Code trending list, published on the 30th of May 2025, which introduces a new fine-tuning method that achieves an accuracy boost of over 22% on a key math benchmark. The paper is titled Logits-Based Finetuning. So the core idea here is to move beyond standard supervised fine-tuning, which often teaches a model just one single correct answer, limiting its understanding of language. This new approach combines that with knowledge distillation, which is a process where a smaller model learns from a larger, more capable teacher model. It does this by using the teacher's logits. These are essentially the raw confidence scores the model gives to all possible words before picking the final one. This creates a richer training signal, and as the results show, it significantly improves performance, especially for science and math models. And for anyone who wants to get their hands dirty with this technique, the authors have released all the official code on GitHub. It looks like it's built using a framework called Llama Factory, and inside the repository, you'll find everything needed to replicate their work. Things like the training scripts, evaluation code, and all the configuration files. Alright, and this figure gives a fantastic visual of how this all works. In the top half, we see traditional supervised fine-tuning. The model might say the cat is on the mat, but if the training data's single correct answer is, the cat lies on the mat, it's penalized. This uses a standard method called cross-entropy loss. Now the new Logits-based approach, shown below that, is much more nuanced. It uses the teacher model's logits to create a whole distribution of good answers, like is, lies, and rests. The student model then learns to match this richer signal using Kullback-Leibler divergence, which is a way to measure how closely its own predictions match the teacher's entire probability distribution. But relying on a teacher model isn't a silver bullet, because what happens if the teacher itself makes a mistake? And this table shows a perfect example of that from the GSM-8K math benchmark. We see a word problem about the ages of Roger, Jill, and Finley. On the left, the powerful teacher model, LLaMA 3.170b instruct. It walks through the steps but makes a critical logic error right at the end, concluding Finley is 55. The human annotation on the right shows the correct reasoning and answer, which is 40. This highlights exactly why the proposed method is so clever. By combining the teacher's logic with the definitive ground truth answer, the student model learns the reasoning style without blindly copying the teacher's mistakes. And this diagram really breaks down how that combination works at a granular, token-by-token level. On the left, you have the ground truth distribution. You can think of this as a one-hot vector, which is a way of saying it's 100% certain about a single correct sequence. In the middle, you see the teacher model's predictions, which are much richer, offering several plausible words with different probabilities. The proposed method then combines these two, and after normalizing them, which just means adjusting the numbers to make them a valid probability distribution, you get the final target on the right. This target preserves the ground truth's correctness while incorporating the teacher's linguistic variety. So now that we understand how that combined target is created, the next question is, what data do you actually feed into this process? And this table answers that perfectly. The researchers tested the LLaMA 3.21b instruct model by fine-tuning it on several different math datasets. And looking at the average accuracy on the far right, you can see that two datasets clearly rise to the top, MetaMath GSM-8K and OpenMath Instruct 2. This is why the authors chose to build their large-scale Logits dataset using these two specific sources. They simply provide the best foundation for teaching mathematical reasoning. Alright, so after selecting that high-quality MetaMath GSM-8K data, the researchers ran a direct comparison, and this graph shows the results. It's an ablation study, which is just a way of testing different components to see what works best. The horizontal axis shows the percentage of training data used, and the vertical axis is the model's accuracy on the GSM-8K math benchmark. The blue line is traditional supervised fine-tuning, and the red line is their new Logits-based method. The takeaway is crystal clear. The Logits-based approach consistently outperforms the old method, and it's more data efficient too. And this table drills down on that final data point, showing the head-to-head results when using the full MetaMath GSM 8K dataset. We're looking at accuracy on the GSM 8K benchmark. The original Llama 3.21b instruct model starts at about 47% accuracy. Standard supervised fine-tuning improves that significantly, up to 54.1%. But the new Logits-based method, it pushes the score even higher to 56.1%, a solid 2% improvement, confirming its superiority. Okay, so we've established the Logits-based method is superior. To build their final, powerful ScienceLLaMA models, the researchers scaled things up significantly by creating a huge new dataset. This table breaks down the full 1.2 million sample Logits dataset they constructed. It pulls from those two top-performing sources we saw earlier, combining about 240,000 samples from MetaMath with a massive 1 million from OpenMath Instruct. And you can see the variety in the descriptions. They're using techniques like problem synthesis and chain-of-thought augmentation, which just means creating more diverse training examples with step-by-step reasoning. By leveraging that massive, high-quality dataset, the researchers were able to create their impressive ScienceLLaMA models. The key takeaway here is that this new Logits-based fine-tuning method offers a more data-efficient and powerful way to specialize models for complex reasoning tasks, like mathematics. It's a clever technique that opens the door to creating highly capable, domain-specific models more easily. That's all for this episode of the AI Research Roundup. Thanks for tuning in, and I'll see you next time.